It's Friday, the 17th of May, 2024. These are the science and space headlines we've been following on Talkin Science for the past month and a bit. Fleet Space Centauri 6 takes to orbit. James Webb probes an extreme starburst galaxy. And unprecedented behaviour from a nearby Magnetar.
This is Trekzone's Talkin Science.
Back at the start of April, I missed the launch of a Falcon 9 rocket from the Kennedy Space Centre. Now, while that isn't all that remarkable these days, part of its payload is. The Centauri 6 satellite adds to Fleet Space's satellite constellation and will play a vital role in servicing the global demand for their mineral exploration solution, Exosphere. Rapid global adoption of Exosphere has been the catalyst behind the company's sustained innovation in space technologies and growth over the past year, their press release says. Over 40 industry-leading exploration companies, including Rio Tinto, Core Lithium and Barrick Gold, have used the technology to complete over 300 surveys for a variety of critical minerals across 5 continents. In 2023, Fleet Space completed a heavily oversubscribed $50 million Series C funding round, doubled its valuation to $350 million and was named Australia's fastest growing company. Centauri 6 has been designed with multiple upgrades to optimise the resilience and durability of the satellite, while also enhancing the overall capacity of Fleet Space's low Earth orbit constellation to support the growing demand for Exosphere. Centauri 6 has greater uplink capacity and redundancy, enabling more resilient data transfer from Fleet Space's satellite-enabled seismic sensors on the ground. The satellite has also been designed with an ion electric propulsion system powered by solar panels to provide thrust in the vacuum of space. Centauri 6's design also leverages 3D printed components, including the 3D printed metal patch antenna Fleet Space pioneered on earlier satellites. An international team led by Astro 3D reports that age is the driving force in changing how stars move within galaxies. Astro 3D, of course, being the Australian Research Centre. We've known for a while that the orderly movement in a galaxy's early life would give way to seemingly chaotic and random movement in older galaxies. But scientists have been uncertain about what causes this, possibly the surrounding environment or the mass of the galaxy itself. But this new study shows that it's neither of those things. It's just getting old. But the earlier work is not necessarily incorrect, says second author Dr. Jesse van der Sunday. Young galaxies are star-forming superfactories, while in older ones, star formation ceases. Our own galaxy, the Milky Way, still has a thin star-forming disk, so is still considered a high-spin rotational galaxy. The study allows astronomers to rule out many processes when trying to understand galactic formation, and so fine-tune models of how the universe has developed. Scientists may be one step closer to unlocking one of the great mysteries of the universe after calculating that neutron stars might hold a key to helping us understand elusive dark matter. In a paper published last month in the Journal of Cosmology and Astroparticle Physics, physicists from the Arc Centre of Excellence for Dark Matter Particle Physics, led by the University of Melbourne, calculated that energy transferred when dark matter particles collide and annihilate inside cold, dead neutron stars can heat the stars up very quickly. It was previously thought that this energy transfer could take a very long time. As the energy of the dark matter particles becomes smaller and smaller, they're less and less likely to interact again. In some cases, the theory was that it would take longer than the age of the universe itself, rendering this heating irrelevant. However, Professor Nicole Bell of the University of Melbourne said the new calculations show for the first time that most of the energy would be deposited in just a few days. An international team of astronomers has used NASA's James Webb Space Telescope to produce the highest resolution image of spectacular exploding stars ever seen. Dr. Deanne Fisher from Swinburne University of Technology's Centre for Astrophysics and Supercomputing led the Australian team. directing the JWST's NIRCam, the near-infrared camera, toward the centre of the so-called Starburst Galaxy to obtain a closer look at the conditions that foster the formation of new stars. Now, star formation continues to maintain a sense of mystery, even though we've had it on Talkin Science a couple of times now, because it is shrouded by curtains of dust and gas, creating an obstacle in observing this process. Fortunately, the JWST's ability to peer in the near-infrared is an asset in navigating these murky conditions. The JWST's NIRCam instrument was well suited to trace the structure of the galactic wind via emission from sooty chemical molecules known as polycyclic aromatic hydrocarbons, or PAHs. Now, these PAHs are like very small dust grains that survive in cooler temperatures but are destroyed in hot ones. Much to the team's surprise, the JWST's view of the PAH emission highlights the galactic wind's previously unknown fine structure. Depicted as red filaments, the emission extends away from the central region where the heart of star formation is located. Another unanticipated find was the similar structure between the PAH emission and that of hot ionized gas. Well, in May 2023, shortly after the start of the fourth LIGO-Virgo-CAGRA observing run, the LIGO Livingston detector observed a gravitational wave signal from the collision of what is most likely a neutron star with a compact object that's 2.5 to 4.5 times the mass of our Sun. Now, neutron stars and black holes are both compact objects, the dense remnants of massive stellar explosions. What makes this signal, called GW230529, intriguing is the mass of the heavier object. It falls within a possible mass gap between the heaviest known neutron stars and the lightest black holes, but the gravitational wave signal alone cannot reveal the nature of this object. However, future detections of similar events, especially those accompanied by starbursts, by bursts of electromagnetic radiation, could hold the key to solving this mystery on a cosmic scale. Many Ausgrav researchers across Australia, including Associate Professor Paul Lasky, were involved in this exciting discovery. Ausgrav is a centre across 8 different universities that receives funding from the Australian Research Council to perform cutting-edge research in gravitational wave discovery. Just 5 days after the launch of Observing Run 4, things got really exciting. That was back on May 29, 2023. Gravitational wave signal passed right through the LIGO Livingston detector. Within minutes, the data was analysed and an alert was released publicly announcing the signal. Astronomers receiving the alert were informed that a neutron star and a black hole most likely merged about 650 million light-years from Earth. Unfortunately, the direction to the source could not be determined because only one gravitational wave detector was observing at the time of the signal. The fourth observing run resumed on April 10 this year with the LIGO Hanford, LIGO Livingston and LIGO Virgo detectors and the Virgo detector, operating together. The run will continue until February next year with no further planned breaks in observing. Also, the sensitivity of the detectors should be slightly increased after the break. Captured by cutting-edge radio telescope technology, a chance reactivation of a Magnetar has revealed an unexpectedly complex environment. Magnetars are a type of neutron star and the strongest magnets in the universe. At roughly 8,000 light-years away, this Magnetar is also the closest known to Earth. Most are known to emit polarized light, though the light this Magnetar is emitting is polarized in a circular motion, where the light appears to spiral as it moves through space. Dr. Marcus Lower, a postdoctoral fellow at Australia's National Science Agency, the CSIRO, led the latest research and said the results are unexpected and totally unprecedented. Dr. Manisha Caleb from the University of Sydney and co-author on the study said studying magnetars offers insights into the physics of intense magnetic fields and the environments they create. Detecting radio pulses from magnetars is already extremely rare. XTE J1810-197 is one of only a handful known to produce them. It was first observed to emit radio signals in 2003. Then it went silent for well over a decade. The signals were again detected by the University of Manchester's 76-metre Lovell telescope at the Jodrell Bank Observatory in 2018, and quickly followed up by Moryang, which has been crucial to observing the Magnetar's radio emissions ever since. Studies of magnetars such as these provide insights into a range of extreme and unusual phenomena such as plasma dynamics, bursts of X-rays and gamma rays, as well as potentially fast radio bursts. Well, that's the news from the last month and a bit that we've been following here. Now, a reminder that Trekzone membership gets you in first releases and first details with a few tiers and a few options. You can help Australia's only science, space and science fiction podcast pick up the pace in 2024. Now, that's in the copy, but it's the middle of May already, so I've got to stop saying that, and I should point you towards the 21st anniversary celebration of Trekzone coming up on July 10. So that's what members are getting, will be getting at the moment, all the lead up to that very, very exciting event happening on July 10th, the 21st anniversary of Trekzone. And of course, don't forget Facebook, Instagram, TikTok, and YouTube shoots, all shorts even, have podcast highlights to find us where you are. For now, this is Talkin Science for the 17th of May, 2024. Bye for now.